In the book. In the book.
Hey.
Yeah.
What's up?
No, he just got home from Singapore. He's got little kids, so he thought, he'd participate by himself.
I was hoping to be here.
If we could have pushed the defense to June, then
Yeah. It would be nice to see. The last time I saw him was at the unnatural proceedings function.
he'll be here in June, so if you're around.
Then I live in the street. Waterloo, just north of
It's going to be standing room only.
Yeah,
You're right. Nice to see you.
Voted most fun ever. Most attractive audience. I know. Overrated. It's all about you, isn't it? Isn't it? The most exciting thing that I heard yesterday about crash. They took pieces of people's guidance. I have to hear. You know, it's all for that outdone. Because all the other, no, I was counteracting what you were doing. I knew it.
Took people's islands and did what?
Well, we might learn about this later. So what they did is they took various regions and they now know the clonal distribution of mutations that are sort of pre-pro cancer. Like the areas of
That's so many people. They never say I don't know.
they never silent.
Me neither.
So I've already got multiple lectures next year.
Yeah, they're really, I don't know what to go through. They're nice. It's a big year for me. What was it in?
I want to get a
I think
picture
it's
of
a
the
nature or
audience.
science.
Oh, wow. That's exciting.
You don't have to know anything about it.
Great.
I didn't read it until Saturday. So I think I dressed it up. You're gonna ask for all this stuff. Really? Like this? Isn't it cool?
It's fascinating.
Right?
It looked beautiful.
You know, Did you see the pictures on
Yeah.
the side? So my mother's like, Kathleen. So I said to she,
That was,
You can finish.
Kathleen stopped talking, so I guess I'll start. I'll just whack her.
you get a brief window.
So it's my privilege today to introduce Jenna to give her PhD defense talk. As supervisor, I get to say a little bit about her and embarrass her a little bit. First thing I want to say is just talking before the defense here, one of my colleagues commented on, wow, what a diverse group of people there are here. Biology professors, computer science professors, lots of family, grad students from other disciplines that we don't even recognize. And I said, well, but that fits the candidate. Jenna's a person who does a lot of things and does them all fully with passion and commitment. So my first experience with Jenna was as an undergrad research assistant. I think it was NSERC USRA, right? And I gave her a project. We had this little hypothesis about how DNA folded to have this little unscrambling process happen. And really beautiful theoretical biology thing that I built up with Nick Stover and Laura Van Weber at Princeton, and it looked like it was really going to work with it. So I handed her a bunch of Fortran code written in the 80s that did molecular dynamic simulations that modify this so that it'll test the hypothesis from the test, and she did without complaint. And we ran the experiments, and null hypothesis. Our beautiful model was just flat out wrong. The data proved, this isn't what's happening. So it's not publishable, not usable, and it didn't deter her in the slightest. And at that point, I thought, okay, this is someone I want to work with. This is a true scientist. Oh well, we got a null result. What's the next thing, right? That's the attitude you kind of have to have in this exam. So at the same time, I got feedback from some colleagues in biochemistry who said, no, you can't have her for grad school. We're keeping her in biochemistry. Well, we'll just see about that. Fortunately, she came to computer science. I'm not going to tell you what she did because she's going to tell you what she did. I do want to also comment on some other aspects of what she did while she was here. How many courses did you teach for us? 4. Jenna taught 4 courses. Won at least the USC Teaching Award for every single one of those courses. Won Dean's Teaching Award and a university-wide teaching award while still a grad student. I still haven't managed to do that after decades as faculty, so that's pretty impressive. And beyond commitment to teaching, she's been a real leader in our research group. She's a leader in the community. She's been involved in more committees than I have time to list here because we just want to hear her talk about me. The most recent example I want to give is that she won Western's 3-minute thesis competition and came in 2nd in the province and is now at the nationals for being able to explain your thesis within 3 minutes, which is really something very difficult to do. I can't explain anything in 3 minutes, as you're seeing right now. So it's been a huge privilege to be able to work with Jenna, and I hope you all enjoy her discussion of what she's been doing.
Well, thank you, Mark, for that very flattering introduction. And thank you all for coming to my public talk. I'm really excited to be at this point. I'll be presenting the work I've done throughout my thesis entitled Using Cellular Automata and Lattice Boltzmann Methods to Model Cancer Growth, Analysis of Combination Treatment Outcomes. And today I'm going to be talking about cancer and what computer scientists are doing to try and attack this problem. And I'm going to go over what the big problem is, because we all know, obviously, that cancer is something we struggle with, but there's specific issues of it that computer scientists are trying to tackle. And I'm going to give you the background information you need to know in order to understand that, and show you what people have done in the past. Then I'll point out what was missing from what's been done and the small piece that I tried to add to this puzzle, and what that comes together to mean. So cancer, what is the major problem? I think a lot of us know the statistics. 1 in 3 people will develop cancer in their lifetime, and 1 in 4 people will die of cancer. In some countries, this is 1 in 2 and 1 in 3. It's the leading cause of death in North America, and jockeys for 2nd leading cause of death throughout the world with heart disease. It's been increasing. Since the 1950s, the overall incidence has increased by 44%. Breast cancer, colon cancer by 60%. Some have doubled, testicular, prostate, and kidney, and some have more than doubled. Malignant melanoma, multiple myeloma, and even some lymphomas. So we know that cancer is bad, but cancer is also complicated. There's over 200 different forms of cancer, and even within one form, such as colon cancer, there's over 11,000 mutations that make up the disease. Cancer varies between tissue, between people, between ages. It's extraordinarily complex, And adding to that complexity is the way that we treat it. So we have over 160 different approved chemotherapy drugs. We have hormone therapy, radiation therapy, immunotherapy, surgery, radiation, just a vast array of ways to try to treat it, none of which are a silver bullet. So we need to try to find the right combination of drugs to treatments for each individual patient. And this is very complex. A nice thing about cancer, though, is it can be boiled down to something that's not quite so complex. So in 2000, Hanahan and Weinberg developed the hallmarks of cancer, which are 8 things that are consistent across almost all cancer. These are changes to our normal cells that take them from being healthy to cancerous. The first is self-growth. So in our body, cells are not always growing. They have to be told to grow when they're healthy. In cancer, the cells somehow are able to continue to grow regardless of these signals. They don't have to be present for the cancer to grow. They also ignore signals to stop growing, or anti-growth signals. Again, our body can tell normal cells to stop growing, to stay where they are, and cancer somehow avoids this mechanism. There's also a safety mechanism built into cells so that they can't replicate indefinitely. They can only get to a certain age. Over time, our cells can accumulate damage, so once they get to that certain age, we don't really want the damage to continue to be propagated, and so cells stop to replicate. But in cancer, they avoid this again and seemingly replicate forever. Cancer cells can even turn on systems in our body that are normally turned off. The blood system in our body is fairly stable and only turns on to create new blood vessels during wound healing or when a baby is being created. But cancer can turn the system on. If the cancer is growing and doesn't have enough oxygen, there's 3 things that it can do. Sometimes it will die at a small size from starvation. Other times it will spread throughout the body to find what it needs. And in the third case, it will turn on this system, angiogenesis, to create new blood vessels towards it. Obviously, 2 of the 3 of these options are very dangerous to us as humans, and so this is a big problem in cancer. Cancer also avoids another safety mechanism, that of cell apoptosis. This is the ability for a cell to commit suicide in the event that it accumulates too much damage. Again, we don't want that kind of damage being propagated to future generations, so the cell will kill itself. But cancer, again, seems to avoid this mechanism. Cancer can even change the way that it creates energy for itself. Our cells make energy from oxygen, but when cancer is growing, oxygen is often limited, and so the cells can turn on other mechanisms that are more inefficient, but also create dangerous byproducts that can be harmful to the healthy cells nearby. Cancer even avoids their own immune system. You might be surprised to know that the immune system acts as a surveillance system that can stop cancer very early on. However, when tumors are actually found, that's because it has somehow avoided this mechanism and the immune system hasn't been able to stop it. The last hallmark I want to address is that of genome instability. So our genes, we take a lot of care to make sure that they aren't mutated, but cancer actually exploits this ability to quickly change the DNA in order to get more mutations that could potentially be beneficial to it. There's 2 that are missing from this slide, and that is the ability to spread. So healthy cells do not just wander off to other parts of the body, but cancer cells can. And also inflammation. So there's tumor-promoting inflammation, where cells are sort of recruited to the cancer area and it gets inflamed. Both of these have been left out of my model and most models in the literature. My model is looking at an individual tumor, so we don't have to worry about spreading. And inflammation can both prevent and assist cancer growth. So it doesn't really have a direct impact that we can add into a computer model at this time. So now that we know a bit about cancer, I'm going to talk a bit about one of the big words in my title, which is cellular automata. Cellular automata is a discrete model that was created in the 1940s by Stanislaw Ullmann and John von Neumann. It sounds complex in theory. You have a group of cells that can exist in any finite number of states, 1 at each moment in time. And these can exist in a finite number of dimensions. There's a set of rules and a set of neighbors designated for each cell that determines what state they're in at every time point. I'm going to walk through a concrete example so it doesn't sound quite so confusing. The top left, we have 4 individual cells. 3 are in the on position, which we represent with a 1, and 1 is in the off position. For each cell, the cell to the left and the right are the neighbors. So for this one, it has an on neighbor and an off neighbor. In order to find the next time point, we look up that current pattern in the table, and it tells us what the cell will become as we go on in time. So for that initial cell, it's currently on. We find the matching pattern, 110, and the new state is to still be on. So we can fill that in for the next moment in time. The next cell we can look at is currently off, and its pattern is 101. That pattern corresponds to a new state of being on. So at the second moment in time, we have this configuration of cell states. I'll walk you through one more example of it. We have an on cell, which now has pattern 111, and that corresponds to shutting off, and another on cell with the same pattern, which turns off. The border cells are treated in a special way that I won't get into, but this here is called Rule 110, and this very simple rule is actually capable of modeling anything in our world that is computable. It's pretty cool, actually. It makes this kind of interesting pattern with these internal structures that are not quite stable but not quite random and are able to model just about anything. And we even see this in nature. So this is a cell or a shell, the Conus textile, whose determination of whether to turn on or off pigments comes by cellular automata rules. So it looks at the cells on either side and what their pigmentation level is and decides whether or not to turn on pigment itself. We even see it in leaves. So the stroma cells in the leaf decide whether or not to absorb gas based on their neighbors and if they are turned on or off. There's even a theory that our whole world is a cellular automaton following these natural rules. It's very exciting. So people have noticed that these cellular automata are able to model real-life properties, and they've used that in the past to model cancer. Some of the early work was done by Cancel and colleagues looking at brain tumors. They modeled this idealized brain tumor called a multicellular tumor spheroid. So they're thinking of a brain tumor as a sphere, which is not that big of an abstraction since brain tumors are encased in our skull. And they looked at 4 parameters. They looked at the overall tumor radius, the proliferative rim thickness, so that's this outside white rim, and they deemed that this is where cells are going to be actively dividing or proliferating. They looked at the thickness of the non-proliferative rim, which is the striped area, and those are cells that are not actively dividing but are not dead. And lastly, they looked at the probability of division. They left the center part to be dead cells, most likely from a lack of oxygen. So using just these 4 parameters, they compared their model to real-life brain tumors of people who hadn't received treatment. They were able to find diagnosis time within 2 days. They were able to find time of death within 5 days, and they were able to predict the total growth fraction of cells within 1 order of magnitude. This was pretty incredible at the time. 4 simple parameters modeled this complex disease in a real human being who had environmental factors, genetic factors, and no treatment within days of their death and diagnosis. And this is one of the beauties of cellular automata. From very simple rules, they produce emergent behavior, which can be very complex and often very close to what we see in real life. People built on these cellular automata models, and one of the most prolific researchers in the area is Alexander Anderson at the Moffitt Cancer Research Center. He developed a similar cellular automaton model, but in each cell there was a feed-forward neural network, so a little bit more complicated of rules. In this network, you don't have to read the whole thing, but basically each cell starts in one position and moves forward. It checks for things like, does it have space to divide? Is it in an area where there's growth factor or growth signals telling it to divide? Does it have enough oxygen? And from this, they were able to predict cancer growth that looked very similar to what we see in real life. The center blue cells are these dead necrotic cells that aren't receiving enough oxygen in their environment. There's a rim of cells that are proliferating on the outside and an in-between layer of cells that are quiescent or not actively proliferating. They found that when there was a lot of oxygen in the simulation, you got these nice spherical tumors. But when there was not a lot of oxygen in the simulation, you got these fingery morphologies on the outside. And along the edges there, you had all different types of cancer, different subclones, they're called. Some were more aggressive than others, particularly on the tips of the fingers. This is because without oxygen, the inner cells were often dying, and the more aggressive cells were going to the outside, pushing the border, trying to find oxygen. It is known that oxygen availability plays a big role in the morphology or shape of the tumor, and that in turn plays a large role in how aggressive a tumor will be. After this, the next paper that I found very interesting was that by Santos and Monteagudo. They looked at a cellular automaton model where the rules were actually impacted by the hallmarks of cancer. They wanted to see if certain hallmarks were more important than others. So they modeled cancer growth with all the hallmarks present. They selected only 5 of them for their model. And this line here, the dotted black line, is how many cancer cells there were in total. Then from the model, they removed each hallmark one at a time to see what kind of impact that would have on overall growth. The red line at the bottom left is removing the ability for cells to avoid that safety mechanism of apoptosis, or programmed cell death. When they removed that, it very much stunted the cancer growth. Other hallmarks didn't have quite a big impact. For example, cell growth, the blue line, only took down the cancer cells by a small amount. Next, they looked at how well the cancer would grow with only 1 hallmark active at each state. That's on the right-hand side. So with just avoids apoptosis, they still had a fairly strong population of cancer cells, and the rest of the hallmarks didn't seem quite as important. So they were looking at the availability of the hallmarks, and Anderson was looking at how oxygen impacted these things. And I wanted to see what more could be done. A statement was made in cancer research all the way back in 1969 that in the most general sense, combinations of therapies, whether drugs and or other modalities, will always play an important role in the management of diseases for which there exists no single, specific, and totally effective treatment. This still defines cancer. We still do not have some kind of magic bullet, and the key here is that we need a combination. What I noticed was missing from the previous models, especially those hallmarks, was what happened if we start knocking them out in combination, and not just individually, while still having accurate oxygen modeling to make sure we see how that morphology and aggressiveness plays out in the simulation. And that's what I wanted to target. So first, I needed a cellular automata model of cancer that would produce a proper-looking tumor. I created one that could start from one healthy cell and would progress to a tumor of detectable size, roughly 3 to 4 millimeters. Once I had this working, I added in the hallmarks. They were part of the rule set for the cellular automata. Again, I only modeled 8 of the 10, ignoring the ability to spread, because I wanted to look at the growth of the first initial tumor, and not modeling that inflammation process. And lastly, I knew I needed to add the oxygen component. Most models model oxygen as simple diffusion, but that's not really as accurate as it could be, so I wanted to make it a little more biologically relevant, and I did this using something called lattice-Boltzmann methods. Lattice-Boltzmann discretizes the space so that you have a grid with sort of fictitious particles. They're not exactly each individual oxygen molecules, but we model these particles and the way they flow. At every moment in time, they can stream and collide with one another and find their place in different areas of the grid. Combining these three things, cellular automata, the hallmarks, and the oxygen, I came up with a model of cancer growth that I'll present. First, I'll go into a little more implementation details for the individual pieces. So the cellular automata, mine is asynchronous cellular automata, so each cell does not update at exactly the same time point. Cells in our body, even cancerous ones, are not dividing at every instant, but rather they divide after some number of hours. So I only updated the cellular automata cells when there was the possibility that they may divide biologically. I used the Moore neighborhood and environmental conditions to determine what the new state would be. So for each individual cell, the neighbors were defined as the 8 surrounding cells. There were 9 possible cell states for the automata. They could be alive, they could die via a variety of mechanisms, including necrosis, so a lack of oxygen, apoptosis, the immune system, they could be quiescent, and there were various levels of aggressiveness that tumors could take on. And lastly, the rules could be altered to represent these mutations. So the rules, for instance, that you need to have growth factor to be able to divide, could be altered if you had the mutation, the hallmark of self-growth. A simple version of what this looks like as a flowchart is that at each time a cell is possible to divide, it would first check for growth factor, or that hallmark of self-growth. If this was present, it would next look to see if it had space. If the growth factor wasn't present, the cell would become quiescent, which is that sort of sleeping, not actively dividing state. Next, we would look at the space. If it did have space, we would check how old the cell was, or if it was ready for division. If it didn't have space, again, it would become quiescent. If the age was right, we would check for the availability of oxygen. If the age wasn't correct, it would just remain for the next cycle. If there was enough oxygen present, we would look for mutations. If mutations occurred in some of those safety mechanisms, like the ability to do apoptosis, then you would get an aggressive cell. If the mutations occurred somewhere else, the cell would die via apoptosis, as we would assume that the mechanism was working properly and would kill off this now damaged cell. The next thing that became a problem was somehow trying to bridge the scales between the biologic cell level and that of the oxygen in the blood around the cells. I've showed you how I modeled the biological cells using cellular automata, but for the blood, I used these lattice-Boltzmann methods. Lattice-Boltzmann models the fluid flow as a discretized version of the Boltzmann equation. It's discretized in both time, space, and velocity. So at any moment, the particles can't just move anywhere they want, but in the 9 velocities, northwest, east, south, and the diagonals, or staying centrally. This is a way of simulating a Newtonian fluid without having to do the full Navier-Stokes fluid dynamics equation, and it's much easier to program. At every moment, it can first do a collision step, where at the same time point, individual cells can follow their vectors of distribution, and they relax to an equilibrium, and then it can stream after that. where the new distributions sort of follow where they were going and find their new position in the grid point. Trying to match this with the biological cells was a little bit complicated. So what we did was made the lattice-Boltzmann grid 3 times smaller than the biologic cells. So every cancer cell had 9 possible cells for the lattice-Boltzmann that we summed up to get the oxygen present at that space. Again, the lattice-Boltzmann doesn't model each individual oxygen cell, so we didn't have to make the sizes work out. These are sort of fictitious particles, but you want to make it smaller so that it's more relevant. Also, we updated the oxygen model every 25 time steps of the regular model. It would be nice to get it even faster, but then the program would never finish. Lastly, the implementation was done in C++. I compiled and ran it on SharpNet using the Intel C++ compiler, and to do one full simulation from an initial cell to a cancerous tumor would take about 5 minutes. A little bit of an outline here of the objects that I used in my model. The cell was really the big player, so it had properties like age, all of the different mutations, how much oxygen it needed to survive or to be actively proliferating. We also had a binary fluid that modeled the oxygen in the blood that had properties like how does oxygen diffuse through human tissue, how much oxygen is needed in various places of the tumor, and then we had events that controlled everything. So an event had a cell and a time point associated with it, and that was our internal clock that made sure cells were updating at the right moment in time. Putting these things together, we got a model of cancer growth that looks something like this. So initially, at the top left, we have the cancer growing. It has a dead necrotic core. It has a gray rim of cells that are not actively dividing, and then lots of healthy blue cells on the outside. As time progressed, mutations started to appear. And any color that is not black, blue, or gray represents some kind of a mutation. There's over 1,000 mutation combinations that could happen, so they're all just colored uniquely. But you can see by the end that we had 2 dominant tumors that are coming out, and most of the healthy cells have been killed off by these cells. The tumor grows to roughly 3.875 millimeters using an average cell size of 25 micrometers, and this takes about 2 years, which is consistent with fast-growing tumors. I looked at the composition of these cells. I wanted to see how the hallmarks made up a healthy, normal tumor. So we have normal cells, like all cancer cells in red, and then cells with each individual hallmark are modeled after that. We found that the most important was angiogenesis, that ability to turn on new blood growth. But second to that was avoiding apoptosis. That was similar to what Santos found in his model of hallmarks. He didn't include angiogenesis, so we don't know whether or not that would have been more important in his simulation. Knowing what they were individually, though, was not really what I was after. What I wanted to know was what happened when you started removing them from the simulation in some kind of combination, groups of 2, groups of 3, and groups of 4. I did this for all possible knockouts. So I did 22 pairs, 56 triplets, and 70 quadruplets. For the pairs, I had this beautiful bifurcation. So what we've done is for all possible pairs of the hallmarks, we've knocked them out. A small selection effectively stopped the cancer growth, and the rest continued on the same trajectory as normal cancer growth. So we saw that some pairs were very necessary for the cancer to grow, and others you could take out and it had very little effect. The triplets and the quadruplets had more complex behavior than just this bifurcation, however. This is a summary chart of the different things I saw. So some triplets and quadruplets basically had no statistical difference. They still grew a tumor. It was roughly the same size, just as aggressive. Some had statistically less cancer. Here's an example where it does have a tumor, but there's a lot of black. Most of the cells are not thriving. It's not quite as aggressive. Some statistically cured the cancer, so none was actively living at the last time stage, and a few actually had statistically significant more cancer. So we were seeing that applying even 4 hallmarks, taking them out of the simulation, somehow allowed the cancer to grow stronger. All of my statistics were done using the Mann-Whitney U-test, and anything significant was less than a p-value of 0.05. This change was also seen in the composition of the individual cells. So things that had statistically more cancer had some mutations that were just rampant throughout the tumor. Ones that statistically cured it effectively lost all of their mutations, and the similar ones that were statistically less looked like a very similar distribution. So to summarize those, we found that with the paired hallmarks, the triplet and the quadruplets, the more you added, the more likely you were to cure the cancer. However, there was the potential to introduce some kind of a treatment that would make the cancer worse. Here I have a heat map of the individual pairs. So whether we were knocking out 2 at a time, 3 at a time, or 4 at a time, I paired up what was being removed. So if I took out self-growth, ignores telomeres, and angiogenesis, I looked at all of those as the pairs that they were, so self-growth and ignorance, self-growth and angiogenesis. And I gave them each a score to see how important they were in treatments that were successful. This dark red square is the hottest, and that's angiogenesis and avoiding the cell mechanism of apoptosis. So that combination of two was most often present in any kind of combination that successfully cured the cancer. But individually, they were not the strongest. So angiogenesis on its own here was not quite as successful in other pairings. Neither was the ability to avoid apoptosis. As an individual hallmark, self-growth was actually most present in pairs that had something successful. So this is not what you would predict. When you look at the distribution of mutations, you would think that angiogenesis and apoptosis would always be the best things to knock out. But when you start pairing them with other things, they can become weaker. In fact, when you pair them to remove them, sometimes you have these effects of having cancer that grows even stronger. I wanted to show that just knocking out the hallmarks was somewhat possible. So for each of the hallmarks that I modeled, there is a drug that is either already available on the market or currently in clinical testing to try and attack this problem. So there is a drug, for instance, that knocks out the ability for cells to develop new blood vessels. But these drugs are not necessarily good independently. So the angiogenesis drug, when it originally came on the market, they gave it to patients of lung cancer. And the patients on the drug died in the same amount of time as the patients who were not on the drug, but from multiple small aggressive tumors all over their body. So they did successfully shut down the process of developing new blood vessels, but this sort of forced the cells to spread and to try and find what they needed. Now it's starting to become available in pairs, in triplets and quadruplets, and actually having positive effects. So the first three are trials that have been completed on pancreatic cancer. This is a common target for combination drugs because there's nothing that currently can cure it. It's 100% fatal, and basically the current treatment, gemcitabine, is only for palliation of the symptoms. But now we're starting to pair it with things. We're starting to pair it, for example, with that angiogenesis inhibitor, Avastin, pairing it with things that stop the ability for it to receive signals. So we're hitting multiple hallmarks at the same time. All three of these showed a statistically significant increase in either overall survival or at least progression-free survival. This combination for metastatic colorectal cancer is currently available and treating patients here in London, and it's the first-line treatment for metastatic colorectal cancer. And that's a combination of 4 drugs. We even have combinations for lung cancer. This is currently being tested for whether or not it's safe enough, but they're hopeful that if it's safe, it'll be more effective than the current individual treatments. So we know that it's possible to do this, and we know that there are drugs that do try to target these hallmarks. So what does this all mean when we look at it together? Well, we've shown that cellular automata and lattice-Boltzmann methods are a great paired method for modeling at the mesoscale. So we're trying to combine the scale of cells with the scale of microscopic particles like oxygen, and we need something that can bridge these together, and this seems to be a pretty good way of doing that. I've also shown that time and space modeling are completed successfully. So my units of time were not just units of time, they were real hours in the cell life cycle, and we were able to get a tumor up to the correct size in the amount of time it would happen in a human. Combination therapy is a great approach, but only sometimes. If you pick the wrong combinations, what you're actually doing is selecting for the most dangerous mutations to be left over in the cell. And again, we've seen this in real life. There's a childhood brain cancer called medulloblastoma, and when it's caught, it has an 80% success rate of survival. However, to treat the children, they give them chemo, radiation, and surgery. If the tumor ever comes back, it's because a few aggressive cells were left over after that, cells that weren't able to be killed by any of those combinations, and reseeded an entire aggressive tumor. At that point, there's basically nothing we can do. And that's what my model was showing, that even with 3 and 4 combinations, you can get the opposite effect. You can self-select for very aggressive tumors that will be worse than just leaving the cancer to grow on its own. Also, I've shown that modeling can potentially rule out certain combinations or classes of drugs. We saw which combinations were always most successful in combination, and which hallmarks were not necessarily very successful, even when paired with a variety of things. So maybe those are ones that we don't need to try clinically. With 160 different chemotherapy drugs, trying all combinations clinically is basically impossible. Individual clinical trials can take 10 to 15 years and over $1 billion. And when they don't work, they're not just wasting people's money, but they've actually seen patients die during clinical trials from combinations of drugs or individual drugs that turn out to be unsafe. So if models like this can become more specific and able to actually rule out some of these combinations earlier, then obviously we'd be in a really great place. And we found that angiogenesis is a key part in combination therapy. Paired with just about any other hallmark, it is very effective. And that drug Avastin has realized that. And we've seen that in a variety of different cancers. When paired, it's very successful. And when given individually, it can actually harm the patient. So moving forward from here, there's obviously lots more that still needs to be done. It would be great to have more tunable parameters, so not just the hallmark rules, so that we can model cancer growing at different initial conditions. My model is for a generalized tumor. It's not specific to any individual type, so I'm not modeling breast or pancreatic. But if you could set the parameters, like how aggressive it is, how much oxygen is available in the environment, then you could start modeling different people's individual tumors. Again, if we had more rule flexibility, then we could have even more mutations occurring throughout the tumor and throughout the growth. If we model more environmental variables like glucose or where the growth factor actually is, or even hydrogen ion concentration, which is a byproduct of that change in energy I discussed, then we'd be able to look at the impact not just on cancer cells, but on normal healthy cells of the growth. And a more advanced model of angiogenesis would really be great. So my current model of angiogenesis is very limited. We do have cells that can turn on the process, and then they act like the conduits through which the oxygen comes. But some models actually pair a model of angiogenesis on top that has the branching structure and looks very much like real vasculature. And adding that to something with accurate oxygen modeling would be very powerful. So that's all. And I'd like to thank all the people who have been instrumental in this work. So specifically my awesome lab, Mark, has been such a great supervisor. Mark let me kind of do my own thing. When I joined the lab, he was not doing this research at all. He wasn't looking at cancer, but he knew it was important to me. And on the first day, he gave me a paper that was by Alexander Anderson, and I never looked back, really. So thank you for encouraging what I thought was crazy. I didn't think you could use a computer to study cancer, which is why I was over in biochemistry, and I didn't really like that. So, sorry. Colin and Francis were my collaborators in mathematics department, which were just absolutely invaluable. Francis provided me with the Lattice-Boltzmann code for that simulation, and it had a lot of equations I would never have understood. So that was very important for this multidisciplinary work. Tyson was my kind of personal debugger over at SharkNet. Catherine Von Mills, Matthew McCann, and Bruce Cameron actually read the whole thesis, and my father found a typo on the front page, so thank you. Philosophy was spelled wrong, and it was a template from Western, so anyway, I would have looked like very dumb. I'm glad. Thank you, Dad. And of course, my examining committee, who may be the only people compared with my proofreaders who actually read my whole thesis, so thank you for doing that. And my family, so thanks a lot to my dad, not just for proofreading, but for paying and doing all the other things dads do, and thank you to all the Butlers and McNeils, that whole clan. You guys have been invaluable, and I know your prayer support has been really appreciated. Thanks, Caleb, for being there every day and doing all the dishes and cooking and all the things I don't like to do so that I could do my work. And thanks to my girls who, I think half of them are in the hallway, one of them's here, but when they're not crying, they're really awesome and bring me a lot of joy, so thank you to them. And most importantly, I just want to thank God, without whom I couldn't have done any of this, and with whom I can do anything. So thank you to all of you, and thanks for attending this talk.
We can take questions from anyone but the formal examiners. You have to wait.
Yeah.
I have actually one question, but it comes in 3 parts. You have simplified the process first by not taking in all the variables, second by using a 2-dimensional cellular automata, and then you use the Boltzmann difference equation instead of the Navier-Stokes, which is really a computational simplification. The simplification, especially the Stanislav Ulam John von Neumann model, which is the 2-dimensional model, may not be as effective as a 3-dimensional cellular automaton model. I know the weather predictions, which used to at some time use 2-dimensional models, were quite inferior to the present 3-dimensional thermodynamic models. So just by doing that alone, you may lose some validity in the modeling. The second might also be question you see your cellular automata rules. Do they really correspond to physiological cellular communication rules? It's, to me, still has to be somewhat verified. But as far as computational, I think by not using the partial differential equation is a good thing.
Me too.
Get involved.
Yeah. Well, I agree with you that it is a vast simplification. And I think that that's okay in some ways and maybe not great in other ways. So that first model that I described was even more simplified, right? We only had 4 parameters and they were able to get biologically relevant results. So I know that it's possible to have a very simplified model be relevant and accurate. Okay. And also we tested our model more so than many of the models in literature. So some of the models in literature, the only way that they say, hey, this works, is they look at a picture of a tumor and they see we have the necrotic core, we have the quiescent rim, we have the active proliferating ring, so this must be relevant. And they don't even look at size or time. So ours matched on those criteria, which is fairly strong for now. The 2-dimensionality would be great in 3 dimensions, and the software is set up that you could add that in, obviously with vastly increasing how long it would take to run it. But 2 dimensions is fairly common in this area because you're often thinking of it as like a slice biopsy. So when we compare it to growth, sometimes we're comparing it to 2 dimensions. So that kind of allows us to have that comparison. But I mean, ultimately, I would love for it to be 3-dimensional, and some of them are, and they have these like great shapes, and you can move them, and it looks prettier as well. So there's just lots of reasons to want to do that. But I think that at this stage, the simplification is okay. Like we are vastly simplifying the hallmarks, but we're looking at the impacts. So I'm not really worried about all the different ways and whether the rules match how the biology gets to that point. We know that the endpoint is they grow without signal, or they ignore signals to stop. And those are binary things that you can easily model in a rule set. So I think that while you do lose some of the accuracy throughout the steps of the model, if the endpoint is still fairly accurate, then I'm comfortable with that for now, for just a PhD. Yeah, Amanda?
So obviously, ideally, what you, like the next step in my mind, at least, with this model would be to then take a series of circumstances of cancer, throw in the parameters and say, do we get what we saw here,
Yes.
right? That sort of thing. Do you think this model is applicable to things outside of directly being inside of humans, so like cell culture or an animal model of cancer, or those things which would be more amenable to those kinds of tests in a more rapid time scale?
Yeah, I think cell culture or an animal model, I think that's possible. The first time we sort of tried to compare this to something, we had an animal model of colon cancer, and at least the shape looked the same, which is what I had been seeing in literature. Okay, if we just have the same rough shape, then we're doing okay. So I think for, say, an animal model, then that would be possible, and I think perhaps better, because if you're looking at a human model, then you're quite unlikely to find one that hasn't received some kind of treatment. And my treatments do not necessarily correspond to whatever they've been having. So if you could have an animal model where you knew initially and then where it got to without any intervention, then we could see if at least the baseline model could do that. And that's something that I would also love to do. Yeah, I think that'd be great. Yes, Ian.
Your homework, your software says which pairings of hallmarks, when suppressed, will lead to improvement or degradation in your tumor growth.
Yeah.
Are those pairing results independent of your choice of a one-time ratio between the cell size and the oxygen size?
So you're wondering if the pairs impact.
Between your cell automata model and your ultimate model for oxygen motion, you chose a one-to-9 grid.
Right. Okay. Yeah.
Is that, did you do a conversion study around that to show that a 1-to-4 grid would work the same, or a 1-to-16 grid, or how did you pick 1-to-9?
So we had a larger, like 1-to-16, something a little larger, and it just would not finish in a reasonable amount of time. So with the lattice Boltzmann, trying to bridge those scales came down to what is possible sort of on SharkNet with the way it was programmed now. So the code is not parallelized. It would be fairly easy at this point to parallelize it, but that was just another step that, wouldn't have been completed in a reasonable amount of time. So I wanted to make sure that it was as fine as we could get it while being computationally feasible. So there wasn't I didn't do like a parameter sweep of all possible because I knew the majority of them would never finish running. So we said, okay, what is reasonable? And most importantly, what gets us somewhat accurate looking results? So we looked at not just the growth of the cancer, but then we also looked at heat maps of the distribution of oxygen. And we saw what we expected. We saw more on the outside. We saw that it was lessening as it went in. So we could tell that the flow of the fluid was still behaving in a thermodynamically correct way with this pairing. So we felt like that was sufficient and feasible.
So that the suppressed hallmark pairings would be independent of grid size?
Should be, yes. Yes?
As we know, the evolution of routine mutation is a big problem around the field of cancer treatment.
Mm-hmm.
So how would you consider that in your model?
So my model applies them at the same point, but you could easily take that to apply them at different moments in time. And so that would be looking at that. And we've seen that. If you apply one treatment, then that might change the composition of cells, and now they become dependent on a different mechanism, and you need to use some other kind of drug. And so my hope was that if you predict that in advance, so if you apply 2 or 3 in the beginning, then you're cutting off those other avenues, and you might never get to that point of having to worry about the change in aggressiveness if you can actually cure it sort of from the get-go. But if that was not feasible, then you could apply one, see the changes in the mutations, see which one is now most critical to the simulation, take that one out, and then you would be looking at sort of successive treatments.
Any other questions? Oh, yeah.
Yeah.
Yeah, I was thinking that these models like the triplets and the quadruplets, etc., like you are taking 2 or 3 or 4 factors to disable them, right?
Yeah. Mm-hmm.
So this is is this more useful in the sense that for the doctors or whoever, like the pharmacists or whoever are designing the medicine, like they will plan to disable those 3 or 4 factors which are found to be very useful or almost good enough to cure the complete cancer.
Mm-hmm.
So whether this research can be used directly by them.
No. So that would be swell, but no. This is more of like a proof of concept. So people have looked at them individually. They tried to find the relative importance. They published it saying like, hey, this is the ranking. But their paper was, they never, the parameters of the paper greatly impacted that ranking. And so I felt like that was kind of obviously correlated to in biology, where our parameters, so the differences in our own body, what mutations we have and where the tumor is, would greatly impact that ranking. And they didn't really get to that point. And so I wanted to look at them not just individually, but in pairs, and then show that these things, these parameters and these pairs change the outcome. And so we need to know more individually about the patient to be able to predict what we could potentially use. So this, as it stands, would probably hurt people, but it definitely isn't at that level. But there are some that are not doing the exact same thing, not looking at the hallmarks, but looking at the microenvironmental variables around the tumor, so very accurate modeling of, say, the acid levels in the tumor or the nutrient levels. And those models are done at the Moffitt Cancer Research Center in Florida, and the doctors will actually come to them. There's both clinicians and researchers, and they'll say, hey, this is what I found inside this person. Can you simulate it? Can you give me an idea of what the best route would be or when it's going to get to this size? And so some models are sort of at that point. None of them are predicting it beyond, the intervention of a human being, but that's the goal, is that we show, hey, these 2 new ways of pairing the model are accurate. The hallmarks seem to have real validity. They're a great way to abstract all these differences in cancer. So let's try and beef up these kinds of models to get to the point of being able to predict the same way that some of the other models are. All right, welcome.
All right, let's thank Jenna again. And if you're not an examiner, I will ask you to leave. Thank you for coming.